Good morning, everybody. First of all, I want to thank Alberto for inviting me here. And it's a great pleasure to be here and telling you something about what I know about the QCD factorization and global analysis. I've been working on the QCD factorization for about 5 or 6 years. And in this, I have 4 hours. And the plan is for this lecture, I will give you an introduction about QCD factorization. It's going to be very basic, but it's not going to be very easy. And then for the next lecture, we'll spend some time talking about the Parton distribution functions, and I will tell you a little bit about global analysis. And for the lectures on Friday afternoon, we will switch from the PDF to, or switch from inclusive processes to exclusive processes. And from there, we'll introduce the generalized Parton distributions, or GPDs. And I will also tell you a little bit about the global analysis of GPDs. And there you will see that the global analysis for GPD is very different from that of PDF, and it's way more difficult, and still quite a lot of efforts are still needed there. But we believe we have a much better understanding of the global analysis of PDF. So for this lecture, we will talk about the QCD factorization. And you may wonder, if you don't work on QCD factorization, why do you want to spend time learning this? And if you, I suppose you already learned something about this from the introduction of QCD lecture, but I will assume you haven't. And the reason why we want to learn or know a little bit about QCD factorization is that we know that QCD has been with us for over 50 years, but we still don't fully understand it. And over the past few decades, if you look carefully, you will see that there are several major advancements of QCD theory, and they are mostly associated with the development of QCD factorization. The reason is, so QCD is a fully non-perturbative theory, but we also know that it's asymptotic free at a hard scale or high energy scale. And therefore, we want to be able to reliably apply the asymptotic freedom to make predictions for the experimental measurements. And the theory formalism behind that is QCD factorization. And if you go into the literature, very often you will find that people apply the perturbative QCD without a reliable use of factorization. And those works are typically not trustable. So if you are a theorist, it's better to know something about QCD factorization so that you can propose reliable things. If you are experimentalists, and it's also good to know about QCD factorization so that you know what you are measuring has physical significance in terms of the comparison with reliable theory predictions. So let's.
Sorry, I had to zoom.
Okay. So what is factorization? When I first learned this, I was very naive. And what I had with factorization was that given me a diagram, I can factor it in 2 parts, a factor, a product of 2 parts. So as given here, we have one simple diagram, and you can always separate here. And by this dashed line, I mean the 2 propagator of this K belong to the lower part, and the upper part only collects this 2 vertices and this intermediate propagator. And this is always doable if you take any diagram, but it's not very useful because you cannot say anything more about these 2 separate factors, U and L. So what we really mean by factorization is that we set some constraints on these 2 factors. we require that one of them, or in here, it's the upper part called U. We call it a hard part. And this hard part should only depend on the short distance interaction, or we say it's a hard interaction. And the other part we call the collinear or soft part, denoted by F here. And this factor should only carry the long distance dynamics, and it should carry all the long distance dynamics. So in this sense, we call it soft. And because in the special case of QCD, we know that for this hard part, we will have perturbation theory. And for the long distance part, we will not be able to see anything from perturbation theory. So we will have to resort to experiments to get knowledge of this part. And we also require that the factorization formula we obtain should apply to all perturbative orders. And I will say more about what I mean here. So the factorization actually was before the advent of QCD. And it started from the deep inelastic scattering at SLAC in 1960s. And we all know this famous story that Feynman has a very nice basic intuition about how this physical process happens. Suppose that now this blob refers to the proton, and here this dot refers to a high energy electron. So now you scatter this electron against this proton at a very large energy scale. And from the perspective of the electron, what you see is that first, the proton has a size. And then the energy, the scattering happens at a very hard scale, so that everything happens at a very local point, a local region. So now you see that if you are this electron, you can only see a very short distance area or parts in this proton. And what's more is in relativity, we know that if things happen very fast, there is time dilation. And what this time dilation refers to is that if you are a parton in this proton, or I should not say parton, if you are anything, a constituent in this proton, the interaction that you feel from other constituents is time dilated by the hard energy scale divided by the soft scale in the proton. So from this picture, we can get the idea that if the process happens at a very hard energy scale, we should generally expect that the short distance interaction decouples from long distance interactions. So this is a very nice picture. But this is not sufficient for us to write down the parton model, or for Feynman to write down his parton model, although he did. But this requires, excuse me, you remove this. So it requires an important input from experiment. And this experiment is a scaling phenomena found at the DRS experiment at SLAC. And we know this happens at the late 1960s. And what scaling refers to is, if you perform this experiment at the DRS, have you learned about the DRS, or deep inelastic scattering? Okay, good. So if you measure the DRS experiment, typically we convert the cross-section we measure into structure functions, or F1 and F2. Here I'm showing you the F2 structure function as a function of Q square. And Q square is the hard scale in DRS. And this is for a particular variable, the X Bjorken. And you see that the structure function does not depend on the Q square. It has a constant behavior. And this happens when Q square is large enough. So this phenomena is very striking. And what it means is this doesn't depend on the scale. So if you increase the energy, it doesn't help you to probe the internal structure of the proton. So the intuition that Feynman obtained from this was that the local interaction that happened here is such that when this interaction happens, the constituent in this interaction is not affected by any other constituents. So that the constituents in the proton behave like a free and massless particles. So this, in this sense, we call these constituents partons, so that they behave like particles. And this picture motivated Feynman to write down his parton model. So already from this, you should know that the great importance of Feynman parton model is that it indicates the strong interaction becomes weak at short distance. So the necessary condition for the strong interaction is the asymptotic freedom. And that's why after the DRS experiment, people started looking for theories that can give asymptotic freedom. And that led to the birth of QCD. But back to the parton model, what Feynman wrote down is that the cross-section, the total cross-section of the DRS can be written as the convolution of two factors. The first factor is the distribution functions of the partons. And then the second factor is the cross-section of this massless on-shell partons with the electron. And the first factor, or we call it parton distribution function, or PDF, is given by the long-distance dynamics. And the second part collects all the hard interactions. So this parton model was greatly successful at that time. And what it tells us is more than what it gave. Theoretically, an important aspect that this parton model told us was that it makes it sensible for us to apply a perturbative approach to understand QCD. Because we know QCD is non-perturbative, but why can we apply perturbative approach? And this has to come from the success of parton model. So parton model tells us that the hard interaction decouples from the soft interactions. So then the whole business of factorization is to take from here and to apply perturbative QCD method to derive the factorization formula. So now before doing that, let's think a little bit about how we should do this and what factorization really means in terms of the theoretical formulation. First, let's think about the proton. If you are a parton in the proton, you know that you are not the only one. There are a lot of partons in this proton, and they interact at all the times. And the second is, when you interact, you are not on shell. You are not really a massless on shell particle. So you are generally off shell because of all these interactions. But if the interaction happens at a very hard scale, then the first thing is your interaction with other partons are time dilated. So they are not so important at the time of this hard interaction. And then because the hard interaction happens locally, if you want a second parton to come into the same interaction, it's highly, highly suppressed in terms of probability. So that means the correction to this formula should be suppressed by the soft scale of QCD over this hard scale Q. And that tells us what we should be looking for when we derive the factorization formula from the theoretical point of view. It's that the parton model should be correct up to power corrections. And that's a great starting point. So let me give you some examples. I will mostly flash through all these formulas so you can get some ideas, but you should not be expecting that you can do all this calculation in your mind as I go. So let's first look at this simplest diagram. I call this the leading order diagram. And this, you can think about this as a perturbative diagram. This momentum P is carried by a parton, say a quark, on-shell quark. And although this is a loop diagram, I call it still leading order because I want to make analogy that this parton or this quark plays the role of the proton in the real theory. And this this gluon is kind of like the remnant inside this partonic target. So from this diagram, so have you seen this kind of diagram with a cut? If you have any questions, don't be afraid to interrupt me and ask. And what this cut diagram refers to is that on the left, that represents the amplitude, and on the right, it represents the conjugate amplitude. And we put them together so that they have the same final state. And then we work in the so-called bright frame using the light front coordinates. Light front coordinates is that for any Lorentz vector, we write it, we make a transformation of the coordinates so that its component has a plus and minus component and the transverse components. The plus and minus components are defined by the zeros and the third component in this way, and the transverse component collects the x and y components. So in the bright frame, this momentum p moved along the z direction. So it only has a plus component, and we call it p plus. And the negative, the minus and transverse component has 0. And the momentum q, which is the virtual photon from the electron scattering, has a plus momentum and a minus momentum. And this, I believe you have seen this in the introduction lectures. And going from here, we first take a look at this cut. This cut across this gluon line sets this gluon on shell. And what this gluon carries is the momentum p minus k. So putting this on shell, we have a delta function. And this delta function, if you work this out, you see that this delta function sets the value for this minus component of this momentum k. And this minus momentum is proportional to the transverse momentum square of this momentum. And I also use the light cone or light front coordinate for this momentum k. And in this diagram, the momentum k is that of this parton, this quark. And you can imagine this as a loop momentum. And we also introduce the variable x as the ratio of k plus over p plus. And from this delta function, we can evaluate the momentum square of this propagator. And you find that it's proportional to the transverse momentum square divided 1 minus x. And we always assume that x is of order 1, not too close from 0, not too close from 1. And from this, you see that the propagator of this quark goes on shell if the transverse momentum of this line goes to 0. And because the propagator is the form of 1 over k squared, if kt goes to 0, you should have something that blows up in the Feynman diagrams. And that is called collinear singularity because the transverse momentum is very small. It's almost collinear with the initial state momentum p. And in perturbation theory, as kt goes to 0, we know now that we have a real singularity, or we have a divergence, collinear singularity. And because this is related to that the parton is closely on shell, it's related to a very long distance and long time dynamics. And around this collinear singularity in the momentum region, we call it collinear region. And we can take the previous slide to write down the form of this momentum k. It has a plus momentum proportional to p plus, and minus momentum proportional to kt squared, and transverse momentum. So we are looking at the region when kt is about 0, or it's very, very small compared to the hard scale q. So in this case, it has a scaling that has a large plus component and a very small minus momentum, and also very small transverse momentum in this form, q kt squared over q and kt. This is a classic or canonical scaling for collinear momentum. And now our task is, so we want to look at this region. And now how do we extract this region from this whole diagram? And the reason we want to extract this is because this region represents a long distance dynamics. So if we put this diagram in the full QCD, and there, this momentum P is carried by a proton, no longer a parton. And the gluon is no longer an elementary particle. It represents a set of collinear lines. So in there, the long distance dynamics represents the non-perturbative piece, and the short distance part represents the perturbative piece. So now because we have obtained this scaling, and the next thing we do is we want to keep all the leading power, but we want to throw away all the subleading power. And by leading, I mean the ratio of KT over Q. So first, the thing we do is when this K flows into the upper part is denoted by this red hook line, and we only keep its plus momentum, or we make this approximation. We replace K by the K hat. K hat only takes the plus component of K. And with this, you know that before this approximation, the upper part and the lower part are convoluted in this momentum K, a fully convolution. And then if we only keep the plus component in the first factor K, you see that they are now only coupled by the plus component, and the minus and transverse components are short-circuited with this lower or collinear factor C. And what this C represents is now a collinear factor, which carries the long distance effect. And it contains both the propagators of K. So it's proportional to 1 over K squared. And this gives 1 over KT squared and further squared. So it carries the low virtuality lines. And also we have a KT squared. And that's the first approximation. And the second approximation is we also need to take a look at the numerator factors of these propagators. And numerator factor takes the form of gamma dot K or K slash. And if you expand this in the light front coordinates, you see that you have a gamma plus K minus term, you have a gamma minus K plus term, and you also have the dot product of their transverse components. And still from the scaling here, we know that only the K plus term dominates. So the thing we want to do is to only keep this term, and we can safely throw away the other two terms. And how do we do this in practice? We define a spinor projectors. And spinor projector, I call it P bar and P. And what this is P bar is gamma minus gamma plus over 2, and this one is gamma plus gamma minus over 2. And the reason they are projectors is that they have these properties for projector. First, if you apply them twice, you get the same effect. And also, the sum of these two is 1. So then we can insert these projectors here, labeled by this arrow here, insert a P bar here, insert a P here. And then what you see is if P bar is inserted here, you have a gamma plus next to the propagator of the quark. So gamma plus kills this gamma plus term, but it retains the gamma minus term. And a similar thing happens if this P is inserted here to the right of this anti-quark line. So then we have this formula. And from this, you see that these projectors keep the wanted term, and it can throw away some of the unwanted terms. And now let's put these two approximations together. The first approximation on the momentum allows us to partially separate the momentum convolution. And the second approximation by the projectors then selects only a few of the Dirac structures. So now with this form, let's take a look again at the lower part. The collinear factor C contains the propagators of the quark. So I write this here, detached from the upper part. This now has two full propagator of the quark, so it can be written as a form of green functions. And this green function is not really like the green function you learned from textbook, because there is also external states P. So we have external states P here, but in the middle we have psi bar for this quark line, and we have psi for the quark line on the left. And the alpha and beta refers to the spinor indices, which now means that this factor C is a matrix in a spinor space. And I have a suffix leading order, which means we only consider the leading order here. So now if we apply the projectors P and P bar, this together with the momentum integrations of K minus and K perp gives us only one Dirac structure. It only projects out a structure gamma minus, and this gamma minus carries the spinor indices alpha and beta, and the coefficient is the function of x, and this we call a parton distribution function. But here it's only refined to the, it's only confined to the leading order. And from there on, we also denote the k plus as x times p plus. So we can write the above formula as this leading order factorization. So we have a convolution of PDF with the hard part. And the hard part takes a particular form that is given by the upper diagram shown here, traced with gamma dot k hat. And what this is exactly the spin average of an on-shell spinor UU bar. So the hard part represents the scattering of an on-shell and massless quark. And this is convoluted with the parton distribution function. So let's take from there and slightly generalize the previous picture. So here I replace the bottom gluon line by a blob denoted by CQ here. And by a blob, I mean all possible Feynman diagram. So everything can happen here. It's a sum of all Feynman diagrams. So then the green function now has a suffix all orders. It's no longer leading order. And we do the same thing by factorizing the upper part from the lower part. And now let me tell you what the projectors do. So on the previous slide, I just told you that with the projector, you only have the gamma minus. But now, how does this work? For any Dirac structure, Dirac matrix with index alpha and beta, we can decompose this in terms of the 16 independent Dirac structures. We have identity 1, gamma 5, gamma mu, gamma 5, and sigma mu. So these are all. And then, because we have an explicit form for P bar and P, if you do this, you'll see that you only have 3 structures left. The first is given by the gamma minus from this term. The second is gamma minus gamma 5 from this term. And third is sigma minus I from this term. So these are actually 4 because this one, the last one, contains 2. I can be either 1 or 2. But in the unpolarized case, if the incoming particle is unpolarized, you only have the first term that survives, and the second and the last term will give you polarized parton distribution function. So we obtain the operator definition for the parton distribution functions. Now, so there we have a Fourier transform over the coordinate z, but here I only have the integration over z minus because I have integrated over the k minus and k perp, which kills 3 components of the z integrals. And the special property of this operator is that you have 2 separated quark fields, psi bar and psi, and they are only separated along the minus light cone, denoted by the coordinate z minus here. And in between, you have a spinor projector gamma plus. And where does this gamma plus over 2 come from? It comes because we want to select this C plus coefficient. And this C plus is the coefficient of gamma minus. And we know that with this decomposition in the first line, you can extract the C mu. And C mu is obtained by simply tracing this left-hand side with gamma mu. So C plus is obtained by tracing with gamma plus over 2. And that's the unpolarized PDF. So with that, we can take a closer look at this PDF. Once this PDF is factorized, I have shown you that this K minus and K perp integrations are fully involved with this part. But if you really work this out, we have seen that we have a square of the quark propagator, and we also have a Dirac trace of the numerators. And this numerator will give us a factor of kt squared. So in the end, you have the form of kt squared over kt squared, this integration. And this integration is from 0 to infinity. And this gives you divergence, right? And now we see that we have two kinds of divergences. We have a divergence when kt goes to infinity. We have a divergence when kt goes to 0. And the divergence associated with kt going to 0 is something we expected, because that's exactly the part we meant to extract from the full diagram, the collinear singularity. But what about the divergence when kt goes to infinity? And that is UV divergence, right? And where does this UV divergence come about? If we look again at the original diagram before we performed the factorization operations, we have this box diagram, which we call the leading order diagram. But here, there is the upper part. This upper part contains a quark line, which is also cut. Cut means it's a final state particle. It's a physical particle. So this cut sets this on shell, and which it gives you a delta function. This delta function constrains the momentum fraction x of this k in these two forms. You don't have to really look at these two formulas. What I want to point to you is there is the square root. And for this to have a physical solution, this square root has to be greater than or equal to 0. And this constrains kt to be smaller than something of the order q squared. So in the original diagram before factorization, kt is bounded by something of q squared. So there is no UV divergence before the factorization. But once we make a factorization, we include the kt integration only with the lower part, and there is no longer an upper part, no longer a cut fermion line in the upper part. So there is no upper bound for kt integration, and that gives us a UV divergence. So it's an artifact. UV divergence is an artifact of factorization. And so we have to remove this extra UV divergence, and we do that by taking extra renormalization. And you have learned from the introduction lecture that the simplest way to renormalize it is to simply add a scale, a cutoff, mu square, for the upper bound of kt integration. And this, what this does is that for the PDF, the kt integration is only up to mu square. So it only carries the physics below the mu square. And the hard part happens between the mu square and the q square. And from this sense, we call the mu square a factorization scale. So factorization scale arises because the PDF has a UV divergence and it requires a renormalization. But this sharp cutoff does not really work well in reality when you actually do the calculation. So we take another approach. We use dimensional regularization plus the MSR scheme. And this is effectively doing the same thing, but more manageable. And for the renormalization of PDF, it happens more or less in the same way as we do factorization, because when you have a UV divergence, UV is kind of like a hard scale. So it's like a hard blob on top. And this has a hard scale. Now the hard scale is just that you replace the Q by another hard scale lambda, and you take this lambda to infinity. So with the bottom part is a renormalized PDF. And now this take a simple, the same factorization structure as the factorization for the original DRS diagram. So this means that the PDF is multiplicatively renormalized. So with the renormalized PDF, take a form of the convolution of the renormalization constant with the bare PDF. And this renormalization introduces a scale, mu square. With respect to this mu square, we have an evolution equation. And this evolution equation is the de Graaff equation. And you have, suppose you have, yes?
Question, the mu, which is the renormalization scale, is that the same one that is introduced in DIMREG?
It,
Or it's just like a similarity in the position?
yeah, it is introduced in DIMREG.
Okay.
Yes, yeah. Yeah, because I kind of run out of time. I don't have much time introducing the many details in here, but feel free to ask me any questions. So I'm going to flash through the following slides. The following slides is just to give you some idea about how we carry through the factorization beyond the leading order. We have seen only a box diagram, and now suppose we have another gluon exchanged here. And this, it looks like a two-loop diagram, but I call it one loop, still in the same sense that we always suppose the lower part, K2, and the gluon line to be collinear with the incoming particle P. We assume this as in the leading order case. And now let's take a look at the upper quark line with momentum K1. And the K1 can be similarly collinear with K2 and P. And we call this region collinear region, denoted by RC here. In this case, the transfer scale is of the same order as the transfer scale of K2. And the other region is that this K1T doesn't have to be small. It can be large. It can be as large as the hard scale Q. So in this case, the whole upper box, I color this in blue. This whole thing can be hard, so it belongs to the upper part, and only the lower part is collinear. So both these two regions need to be taken into account. And we start with the first region, RC. For RC, only every line in this bottom is collinear. So we do the same approximation we did before, denoted by this hook line. Hook line it indicates a momentum approximation and a spinor projector here. But for the second region, we have to make approximation here because all the upper part is hard. But then you notice that these two diagrams, these two approximations actually contain an overlap, because even though you apply this approximation here, you cannot forbid the upper line from going collinear. So we have to subtract this extra region to avoid double counting. And that subtraction takes the form of, you first apply the approximation here as in the first diagram, and then you apply the approximation here. And these two needs to be put together. And now this is the one loop factorization, and we have done the leading order factorization. Now let's put them together. The leading order factorization summed with this gives us the same hard part. The hard part is the same, but the lower part are different. The first diagram gives you a leading order PDF. The second diagram gives you a next to leading order PDF. So these two sum up, and they have the same hard part. And for the second one, we have a hard region with a subtraction of collinear subregion. And this gives us similar hard part, but this hard part is the one loop. And this one loop hot part contains a further subtraction of the collinear subregion. And this whole thing is convoluted with the leading order PDF. And as I have indicated here in these two blue boxes, the momentum integration of K minus and K perp are fully included in the PDF. So that picture seems to generalize straightforwardly. So, and that's indeed the case. If we only have the diagram of this sort, we have the clear separation of the upper part and lower part, and you can insert the intermediate ladders here, and you can insert as many ladders as you want. So if we only have this kind of ladder diagrams, or that if only this kind of ladder diagrams are important in the sense of being leading in terms of the power of the soft scale divided by the hard scale. And we can carry out this procedure in relatively straightforwardly, although not technically so simple. But I'm writing down the result here just to give you an idea. The left part contains a summation over this intermediate blob K0. And there is a T hat. T hat is a projector or approximator that we inserted, denoted by the hooked line before. This applies certain approximations. And the second factor denotes by the PDF. The PDF contains all the diagrams. So that's what we mean by the factorization. It applies to all orders. And the hard part contains the subtraction, denoted by this 1 minus T hat. So, but there are other leading regions if we take the Feynman gauge. The above story holds if we use the light cone gauge. And if you do not have a gauge boson, it also applies. But in QCD, if we work in the Feynman gauge, we have other diagrams. And this diagram is shown here. You have a gluon that enters the hot part in this way, and this gluon can be cut or uncut. And in this case, we still assume that the bottom part is always collinear, but this upper part, the K1, it can be collinear, it can also be hard. So there are two regions. And if the hard region is the only one that should be taken into account, then this whole triangle blob should belong to this upper blob denoted by H here. And this reduces to the upper part, to the upper scenario. But if this K1 can be collinear, and if this collinear region is not so small, we have to deal with this region. And this is the complications in factorization, or it's a major, the key point in the factorization, which is associated with this pinch singularity. And how to understand this, I'm giving you a simple, very simple example as shown here. We have a triangle loop, and this is a virtual loop. K1 is the loop momentum. There are three propagators, K1 and K2 minus K1 here. And there is another one in the top, which is K1 plus Q, so denoted here. And if we look at this Feynman integrals, important point is that there is an I epsilon prescription. And what is I epsilon prescription means that is that we should think about this integration as in the complex space. So if we look at the K1 minus integration first, these three propagators give us three poles for this K1 minus. And the first one from the upper propagator, I call it K1 hard, K1H minus. And from K1 squared, I call it K1Q. From the gluon line, I call it K1G. And these three poles have their epsilon prescription indicating to which side they lie in the complex plane. And the region we are interested in is that X1 and X2 are not so close. They are not so close from 0. They are not so close from 1. So they are of order 1, and the X1 minus X Bjorken is positive, X2 minus X1 is positive, and X1 is positive. So now in this region, let's think about the case when the K1 is collinear. The transverse momentum is much smaller than Q. So then I have these 3 poles from these 3 propagators, and the 2 poles from the quark and gluon lines are very close to each other. But they lie on opposite sides of this real axis, and they are very close to 0. They are very small. And the other pole from the upper quark line is the pole that's very far away from the other 2. So for the integration contour of the K1 minus, we can deform the contour to get away from this pole. So the propagator is not so close to 0. You have a regular integrand. But the other 2 poles, they are pinching the integration contour. So no matter how you deform, you cannot get away from these two poles. And that's what we call a pinch. And around these 2 poles, the 2 propagators, the quark and the gluon, are very, very small. And that gives you a very large integrand, which is likely to give you a divergence. And that's why we call it pinch singularity or pinch divergence. And now in the other region, when the K1T is not so small, let's say it's of order Q, and then these 2 poles will be away from 0. They are also of order Q. So now you can safely deform the contour to get away from all these 3 poles. And in this case, you do not get any singularity. And this simple analysis should give you an idea, which is very important to the business of factorization, is that whenever we consider a loop momentum, we can always deform the contour unless we are forbidden by the pinched poles. So if we are able to deform the contour, we enter the hard region. But if we are not, we enter the region by the region pinched by the on-shell poles, which we call the pinched regions. And in this particular case, the pinched singularity is characterized by the limit that K1T goes to 0. And in this case, we have the momentum scaling, the collinear scaling for both K1 and K2, and they are both small. And now, so I still have a few slides. I know the time is up.
Well, we can take 5 minutes, Max.
Okay, yes. So for the following slides, I'm also just trying to give you some ideas about how we deal with this and what new phenomena occurs. And what occurs is, if we want to extract the contribution from this collinear region, that we say K1 is collinear, and now we see we have a numerator factor which we have been left unnoticed. And this numerator factor is a chain of Dirac matrices. And now from this gluon line, this gluon connects the collinear vertex here with the hard vertex here. And the hard vertex is a gamma rho here. And collinear vertex is also gamma rho here because we take the Feynman gauge. And the second gamma rho is surrounded by 2 collinear fermion propagators, gamma dot K1 and gamma dot K2. And we have known that both have the leading component proportional gamma minus. And surrounded by 2 gamma minuses, this gamma rho can only be gamma plus. And therefore, to extract the leading contribution, we need to only keep the plus component for this upper, or for this gamma rho, or the plus component for this gamma rho. And that takes us to these approximations. So suppose we write this diagram in terms of upper part H with the lower part, which I call J, and they are contracted in the gluon vertices rho. And we only keep the plus component. And the plus component can be, I can insert a factor here, K1 plus and minus, and N is an auxiliary vector, which I introduced to only carry the minus component. And this is an identity. And this K1 plus contracted with this H plus, it gives you a momentum K hat contracted with this H. And in this harder part, we know that we have approximated K1 by K1 hat, which contains only the plus component. And the other factors is grouped with the lower factor, the collinear factor. So now the first factor takes the form of K dot diagram, which is the form of a wired identity. And the second factor will give us an eigenfactor. So applying the wired identity, I introduce this hook indication for this approximator and this triangle for the application of wired identity. Using the wired identity, you can factorize this gluon from the hard part. And this gluon is then collected by an line or a Wilson line. And from this, the upper part is the same as what we have seen before in the leading order, but the lower part is something new. It's a modified collinear factor now with the Wilson line. And this Wilson line, I have no time to introduce the Wilson line to you, but the Wilson line is operator definition for this line. And what about the other region? We have a hard region. A hard region is that is around here when the momentum is around here. And hard region has to contain a subtraction of this collinear region here. And this gives us similarly an upper part with the original diagram, but with the subtraction of the collinear subregion. And the lower part is the same leading order PDF as we have before. And it's a similar story applies to the other diagram when the gluon is cut. And we also have two regions, collinear and hard. For collinear region, we apply the same approximations and it's factorized in the same way, except that the gluon is now collected by Wilson line on the right of the cut. So this gives us still the same upper part, but for the lower part, we have addressed PDF with the Wilson line on the conjugate amplitude. It's now associated with psi bar. So the exercise I give you is, first, you can take the previous wisdom to justify the approximation we made here. And second is, we have only considered the collinear region here. And if you also consider the region when K1T is large, you can write down the proper subtraction structure and the factorization result. And that carries through to all orders. In the all orders, we can, for each region, we have an upper part and lower part, and they can be connected by an arbitrarily many gluon line. But these gluons have to be, have to take a particular polarization that we can apply the wired identities. And in the end, we have an upper part and we have a lower part with two Wilson lines, one on the left and one on the right of the cut. And from there, by including all the diagrams with subtraction for subregions, we can arrive at the factorization formula. And in the end, we have this factorization formula. And now this factorization formula seems to take the same form as we saw on the first slide from the Feynman-Parton model, but we have something new. The first thing is we have a factorization scale mu. And second is we have an operator definition for the PDF. And this operator definition contains psi bar and psi separated along the light cone, and they are connected by a Wilson line. And for the hard part now contains all order diagrams, but they have been carefully treated to have subtracted all the collinear subdivergences. So they are infrared finite. And that's what we gain from a careful treatment of factorization. So I can only tell you this much about factorization, and I have only talked about DIS. But now, to summarize, we can go back and think about what we have done. So I have motivated the factorization from the Parton model, from the scaling of DIS. And this motivation is for the full QCD with non-perturbative and perturbative dynamics. But later on, we only discussed this factorization for perturbative diagrams. So, and what we have done is we factorized all the pinch singularities from the hard part, but for perturbative diagram and to all orders. And in doing this, we are implicitly identifying the perturbative pinches at low virtualities with the sensitivity to non-perturbative dynamics. And also, we assume that the hard coefficients we obtain from the perturbative analysis apply also to the hadron scattering in the full QCD. And now, those can be regarded as the basic assumptions of factorization. But now, are they justified? And how are they justified? Because we are using perturbative method to treat the non-perturbative or full QCD, it's not really possible to justify the assumption from the first principle if you do not know anything about non-perturbative QCD, and we still don't know this to today. And therefore, this has to be justified from the comparison to experiments. And in doing this, we have to always remind ourselves that factorization formula, although it's very powerful, it's also kind of special because it reduces unknowns to unknowns. We don't know how to calculate hadron scattering, but we reduce it to something we still don't know. The PDF, we don't know. We can write down the operator definition, but we don't know the actual values. So they have to be fitted from data. So the predictive power of factorization comes from the universality of these non-perturbative functions. And it is this universality that allows us to make predictions and compare to experiments. Therefore, the factorization is really justified first by the scaling phenomena, which we discovered in the first day of QCD. And second, to today, it's justified by the tremendous success of the global analysis of PDF. And that I will talk about in the next lecture. We already know that we're only a handful of parameters we can fit to thousands of data points with great precision. And that's why we trust the result of factorization. And that ends this lecture. Thank you.
Any questions?
Yeah, so from an experimental perspective, so when we say something is collinear to something, does it mean like they're traveling in the same direction almost and there is no almost transverse kick?
They're the same, right?
Yeah.
So, so by the collinear here, I mean mostly in the Feynman diagram level, because the Feynman diagram intermediate particles are not observable in experiments, right? But in experiments, you also have collinear particles. Particles can travel in the same way. Those are also collinear. They are the same. Yes.
Okay.
I had a question with the spin projectors that you use in that approximation.
Yes.
Is there like a physical intuition of what type of approximation that's making? I mean, I guess like with the linear approximation, like it makes sense in terms of like high energy electrons like hitting the proton. Is there a similar way to think about the spin projector approximation?
I'm not sure what exactly you're asking. So you're asking the physical significance of the projectors?
Yes.
The projectors, to put it simply, it projects the particles on shell. And when you think about the spinner, Dirac spinner, when the momentum is very, very large, closely to be light-like, the two components of the spinner is close to zero, and the other two components are very large. Right? So the projector is taking out the large component and throw away the small components.
Can you explain like one loop factorization of DAS if it is more than like one region? Like how can we consider the momentums?
You're referring to this one?
Yes. The next one. I think. Yeah, this one.
And so this one or this one?
The second one.
Second one, yes. So if you naively look at this diagram, if you want to factorize this, and the first question that pops up is, where should you factorize, right? Should you factorize here or should you factorize here? And they are both possible, but they depend on which region the upper momentum K1 lies in. So if K1 is collinear to K2, then all these lines, K1 and K2 are collinear. They are collinear, so they has to be, they need to be factorized to the bottom part. And that's what we do here. We insert a projector here. We approximate the momentum K1 as it enters the upper part. And we insert a spinner projector to project this line on shell. And that's what we do here for the region when K1 is collinear. But K1 doesn't have to be collinear, right? K1 is a loop momentum. It can take whatever it wants, right? So it can also be hard. By hard, I mean its transverse momentum is not so small, it's large. And if you do, there is another thing which I did not have time to talk about, is a power counting. You can do a power counting in both regions and you find that they are both of the leading power. So in this case, this region should also be taken into account. And because now it's hard, it should be included in the hard scattering. It should be in the upper part. So we need to insert the projector here. And projector here only approximates K2 as it enters the upper part and inserts a spinner projector here to take this K2 on shell. But if we only sum up these two diagrams naively, you have a double counting because you have originally only one diagram, but now you reduce it to two diagrams. And this two diagram has a overlap. This overlap region has been taken into account twice. And to see that, you can look at this diagram. Although I applied the projector here, this doesn't forbid the upper box from going collinear. K1 can still go collinear. And this region is still leading, right? But this region has been taken into account by the first approximation. So you need to introduce a subtraction. And this subtraction is to remove the double counting region. And it's because now you see you have the same projector here, but you need to we have to do this by hand. You remove another collinear region from this upper box.
It's like difference between them is like you are adding and then subtracting.
Yes,
Three,
yes,
basically.
yes. And this subtraction structure is not unique to factorization. It's also there if you do renormalization. We know when we carry out the renormalization to high orders, to arbitrary orders, not only do we have to introduce a counter term for each new divergence, we have to subtract all the subdivergences.
We applied this one to polarized stuff also.
Polarized proton?
Yes.
Yes, yes. And so the argument here does not care about the polarization of the incoming particle. And as we have seen somewhere, yeah, here, the polarization enters from different terms here. If we keep only the first term, this only applies to the proton being unpolarized. And the second term is for a longitudinally polarized proton. And the last term is for transversely polarized proton. And their coefficients, delta C plus and T plus I, can be extracted by a similar way. You just replace this gamma plus by, suppose for the second term, you should have an additional gamma phi. And for the last term, you should have a sigma plus I. And those are how polarizations are introduced.
Thank you.
Yeah.
Any more questions?
So is this process more or less analogous in the case of the TMD factorization?
Sorry.
So is this process, all the steps that you showed, is this more or less similar in the case of TMD factorization? So this is general for all regimes.
Not exactly. So TMD, the basic methodology of this still applies to TMD, but TMD is a kind of a special kind of factorization because TMD requires you to observe some low scale, like the QT scale in TMD, and at the same time as you observe a hard scale. So you observe large Q, you observe a small QT, and both are observed. And there you have a TMD. But here we have only one hard scale, the Q scale, right? So this doesn't lead to TMD, but TMD can be obtained by generalizing the argument I showed you here.
Thank you.
Yeah, unfortunately, I won't have time to talk about TMD. Unfortunately or fortunately.
All right, we take a 10 minutes break and then we convene at 10:30.